Okay, we've already talked about Lewis structures. And so the very first thing that you always want to do is try to count up all your valence electrons. Then you're going to put your valence electrons around your atoms. And you know that the guy that's going to be the least electronegative is going to be in the center. You guys remember how to determine that? The chart, that's right. The chart, exactly. So we're going to use the electronegativity chart to determine who's in the center. And then with this step, everybody has to get the top step, right? Except for hydrogen, you know, hydrogen only wants 2 electrons. And so long as you remember that, you're going to be okay. Now, there'll be an opportunity for extra credit points because I did show you guys how to do the charge using the formal charge. I went over it early on about the formal charge, how to calculate the formal charge. If you guys remember it, great. If you don't, then hey, you just miss out on extra credit points. So I'll slide over. Maybe that'll help. Is that better? Or is it have something to do with Zoom? If I move over to a different mic, is that better? That sounds good. Okay. Don't trick the word.
This one, wasn't it? Barry?
Yeah.
Barry or whatever. He's completed.
Okay, so is it still good? Can you hear me now? Is it better? Okay, good. Thank you. So after you actually figure out everything that's octet, you want to confirm that, right? And that's it. I mean, it's not much to it. So, everybody has chapter 13. So nitrogen, how many valence electrons does nitrogen have? 5. It has 5. Okay, hydrogen. How many valence electrons does hydrogen have? 1. And we have 3 hydrogens. So 3 times 1. So we have a total of 8 electrons to work with. Okay. So how can I make that work? Which packet is it? 13.
You could draw bonds from N to all the H's, and that would give each hydrogen 2.
Okay, so just make a bond between here.
Yeah, on all of them.
If the audio is working. Okay, So that's 2, 4, 6, 8 around the nitrogen. That's 2 around the hydrogen, 2 around the hydrogen, 2 around the hydrogen. Piece of cake. Okay, so we have hydrogen carbonate ion. Who's going to be the center atom? Well, let's count all the valence electrons first. So hydrogen has how many valence electrons? Carbon has how many valence electrons? 4. Oxygen has how many valence electrons? 6. So we have 3 oxygens. So 3 times 6. And then we also have this minus here. What does that mean?
You have to add one.
I need to add 1 extra electron. That's right. Okay, so we add them all together. We have a total of 18, 20, 24 electrons. Okay, so who's going to be in the middle?
Carbon.
Carbon.
And it's carbon because the electronegativity is less than oxygen? Is that
Yes,
why?
that's right. Yeah, and also carbon has an affinity for the middle. So if you have a choice, carbon will always choose to be in the middle.
Just like the H always is on the outside.
That's right. Okay. And then oxygens. Each have 6. Okay. And then the hydrogen has 1. Okay, is there any way that we can make this work?
Bond between each oxygen and carbon
I
and
forgot-
the
I
hydrogen
forgot my extra one. So you said a single bond.
between the oxygens and the carbon.
Okay, so let's do that. Okay, so that's 2, 4, 6, 8 around the carbon. That's 2, 4, 6 around this oxygen. 2, 4, 6, 8 around this oxygen. 2, 4, 6, 8 around this oxygen. So you're saying Single bond here. Okay. So that's 2, 4, 6, 8. 2, 4, 6, 8. So that's still not gonna work out for us.
You can do a double bond with oxygen and carbon.
Okay, so if we do a double bond with oxygen and carbon. Okay, so then that's 2, 4, 6, 8. 2, 4, 6, 8 around the carbon, 2, 4, 6, 8 around this oxygen, 2, 4, 6, 8 around this oxygen, and 2 around hydrogen. So we need a total of 24 electrons. That's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. That's all 24.
So when you do a bond, does it take one valence electron from each one you're bonding from, or does it?
No.
take two?
It doesn't matter. It doesn't matter because the electrons are mobile and they're up for grabs, right? And so they want to try to find the more stable structure. So they're willing to move any way that it's necessary to make it work.
So it's not like, no, take away and then put over here.
No. Good question. Though. Let me repeat the question. Did you guys hear the question? Yes, no, maybe.
No,
No,
Okay, so the question was, when they share electrons, are they taking one from each of the different atoms? And the answer to that is no. All the electrons that are valent are accessible. So you can end up taking 3 from one atom and just 1 from one, long as everybody reaches this octet. Okay, did everybody get this down? I said that you don't have to take one electron from each atom. So we're sharing electrons. Take 3 from one and 1 from the other. It doesn't matter long as everybody reached their octet.
What is the last one you said, octet?
Octet. I'll spell it for you. Meaning that it has 8 around it, or it's stable. Okay. Oh, and I forgot to put the bracket around it, my bad. Because it was a negative ion. Okay, the next topic that we're going to be talking about is the resonance structure. Resonance structure is just basically the fact that electrons are constantly moving. And so if you have identical atoms in a spot, and you can have a double bond in one spot and a single bond in another, the electron is going to be able to move between those. And that's what is called forming a resonance structure. The fact that the electron could go from one of those atoms to the other one. Okay. So let me give you an example. Okay, so here we have 3 oxygens. Okay, now the resonance structure is the fact that the double bond is located here on one of the oxygen, then it's located on this other oxygen, and then it's located on this other oxygen. Because the electrons are mobile, they're going to be moving like that because the pull on all of those are going to be the same, right? And so the electron is going to be essentially moving the double bond from different spots. Okay, so you'll have one situation where it's there at one point, another situation where it's, on the other oxygen, and another situation where it's on a different oxygen. So has a same structure, right? That's always going to be the same, right? It's just the fact that the electron is able to move from each of the different oxygens. So that is a resonance structure. Okay. Now an isomer is different. An isomer is it's two compounds that have the same molecular formula, but they have a different shape. Okay. So give you an example. Here, let me get a professional drawing. Otherwise, we'll be here all day waiting for me to try to get this drawing. Stop real quick. Okay, so we have glucose and fructose. So this here, each of these spots at the end of this represents a carbon. So both of these are, their chemical formula is C6H12O6. Okay, so they both have the exact same chemical formula, but the structure is that this one is a 6-ring structure. This one is a 5-ring structure. Okay, exact same chemical formula, but their structure is different. How they behave chemically is going to be different as well. Okay, even though that they have the exact same chemical formula. So those have to show this, so that has this. But they're going to have different properties, chemical properties. Different physical properties. So their Bellevue temperatures are different. How they're going to react is going to be different. Okay. So this is an example of an isomer. Isomer basically means it has the same chemical formula, but different chemical structure. Okay. Okay, so we've talked about the electron pair geometry. And so that's going to be the valence shell, electron pair, propulsion. Good. Basically, electron pairs are going to pair each other. So in other words, they're going to be far away from each other as possible. And so that's the reason why you're going to have them distributed at different poles. So I'll show you what I mean by that here in a minute. The thing that we want to keep in mind, you want to pay attention to the angle where they're going to be. So for instance, if it's a linear structure, it's going to be an angle of 180 degrees. If it's a tetrahedral, it's going to be an angle of 109.5. Okay, and then I'll show you some of the other ones as well too. Okay, so a tetrahedron is basically something that has 4 sides. So they have four-sided solid having congruent equilateral triangles or bases. So I can give you an example. Okay, so this here would represent linear, the very first one, meaning that there's two electron pairs on both sides, or I would say two attachments. And so it's going to be a linear structure. The angle between the electron pairs is going to be 180 degrees. This here is trigonal planar. So in this case, you have three electron pairs that are 120 degrees away from each other. And this last one is tetrahedral. In this case, we have four electron pairs, and they're all 1.5. Okay, so this is just basically me showing you with a balloon. If you had two atoms that were attached to each other, you would have a linear pair. The balloon is kind of representing the electron densities. So. This here is trigonal planar. So in this case, they have three attachments, and that's going to be 120 degrees. Doesn't have two attachments. So in this case, this guy's going to be 1.5 degrees. It's going to be tetrahedral. Okay, this is that same chart that's in your packet. You gonna take a picture of it?
It's a little blurry on our packet.
Can't help it. You know, the packet was shrinking before it got photocopied.
Told you.
At least you show up.
Okay, so here you can see that we have the electron pair geometry, and that's shown over here. And then we have what we call the molecular geometry, and that's shown here. Okay, so now the molecular geometry is what we're going to be able to visualize. Okay, and the electron pair geometry, you don't see the electron pairs. So in the case of, let's say, the molecular geometry, if we have two attachments to that center atom, in other words, we have an example like BeF2. So in this case, this guy is going to be linear, just like what we saw with the electron pair geometry. In the case of, we have boron tetrafluoride. In this case, we have three fluorines that are attached to the boron. In that case, it's going to be trigonal planar because we have three attachments. Okay. Gotta clear this right here. So here, when we have sulfur dioxide, in this situation, we're forming a double bond. We have a lone pair on that center atom, and we have a single bond. Now, the double bond isn't that geometry. It's just going to seem like it's an attachment, and that's it. So the geometry is going to just simply be bent in this situation. And so you're going to have a bent or angular structure. Okay. Yes.
So the SO2, why is it different? Like what do they look different? Bond stick model and then different like
Space filling.
so one's bent and one is trigonal.
Well, no, this is actually bent as well.
Right.
Yeah.
Why does it show up like next to it on the side?
Right here,
No, a little bit more that way.
right here,
No. Oh,
this
Yeah.
way. Okay, so the reason why it's showing up, because there's 3 attachments, right? The thing is that the electron pair in case of the molecular geometry is not visualized. You don't see the electron pair. So all you see this, right? This is gone in this case. Okay, so you just see this part right here. So you see the bent structure. Okay, so the electron pair geometry, you see everything. You see electron pairs and you see the atoms attached. In the case of the molecular geometry, what we actually see, what we visually see, is going to be just those that are not the electron pairs. So you don't visually see the electron pairs. Yes. So, and then that's why the structure looks bent. Even though that there's electrons pairs, the electron pairs are pushing them because they actually exist there. So that's going to change that angle. Okay. So does that make sense? Do you guys get that?
so those 2 3 valence electrons, they show up in the electron pair.
You mean the lone pair?
The lone
Pair. Don't say
Yeah.
2 free valence electrons.
The lone pair is shown in the electron pair, and then in the Lewis diagram, it's not.
That's in the molecular geometry, it's not.
Like,
Yes. The Lewis diagram is that show. But the Lewis diagram is that's the molecular geometry. Okay. So the next one is tetrahedral. So in the case that we had the 4 lone pair that were attached to the center atom, in that case, it's going to be tetrahedral, 109. Now, if we have 4 atoms that are attached to the central atom, then it's also going to be tetrahedral. Okay. Now, here's a situation where we have 4 electron pairs attached. And then in this case, we only have 3 electron pairs, and we have 1 lone pair. Right? So this is the case of nitrogen and ammonia. Nitrogen. Long day. It's the case of ammonia. So in the case of ammonia, the nitrogen is going to be in the middle. It's going to be our center atoms, and we have the hydrogens on the outside, and it's going to have that lone pair up top. The electron pair geometry would be tetrahedral, 4 attachments. But the molecular geometry, we don't see that upper attachments. So it looks like a little pyramid. It looks like a little pyramid going. So we call it trigonal pyramid. Okay, so we built this last week, right? If you guys remember, on Monday. Today's Wednesday, right? We built this on Monday. That was last week. Yeah. It was last week. It was last week. Okay. So in the last case, we have, again, we have 4 attachments. Okay. So, and that's including all of our lone pairs. And this is the situation with water, where water actually has 2 lone pairs on the oxygen, and then you have the 2 hydrogens attached to the oxygen as well. So if we looked at the electron pair geometry, it's going to be tetrahedral because there's 4 attachments. But if we looked at the molecular geometry, because we don't see the lone pairs, it just looks good. Okay? And so that's actually okay. So this is just basically showing us everything that we just talked about on that table, that it broke it down, and it gives you examples of different compounds that shows that. So up top, this is the molecular geometry. Right here, we can see that they're all 4 attachments. So essentially, they're all tetrahedral for the electron pair geometry, but their molecular geometries are different because here we have 4 real attachments, 4 atoms that are attached to that center atom. This one, we have 3 attachments, and then we have the lone pair. So that's how we go. And then the next one, we have two real attachments and two lone pairs. So that one is going to be banned. Because we want to try to show things 3D, and I have third grade handwriting, and so my structures of my ball and sticks are always kind of wonky, if you can't tell, right? We often will use something called the wedge dash system to draw diagrams. And so when you're using the wedge dash systems, the way that you want to think of it is the dash is going to represent the element that is moving away from the center atom. So it's like in the back of the center atom, right? Then you're going to have the one that's in the front of the center atom, and that's going to be your wedge. Okay, so let me show you what. And then the one that's in the same plane as the center atom, that's going to just be the wedge. So okay, so here, this is an example of the wedge diagram. And so we know that in this situation, this guy is going to look very much like ammonia. There technically should be a lone pair up top, right? So if we drew the Lewis structure, it's going to be like this. And I feel like my ink is running out because every time I press something, nothing's working. Okay, so then we have Cl. Okay, so in a situation like this, we basically have the nitrogen in the center. You have Cl, 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 right? So when you draw the Lewis, the wedge dash structure, the Wi-Fi or the little lines, that one is going to the back. It's the back of the, okay. This first one, the wedge, that one is coming out towards us, okay. And then this one would be in the same plane as the in itself. So then it's kind of like okay, so it's like this arm here, right? This is going to be the one that's in the same plane as me. Okay, this is going to be my arm here. It's going to be what's in front, and then my arm back here is going to be what's in the back. Okay, so so that would be the structure that would. So we have one that's in front, one on the side, and one in the back. Okay, so that's the way that structure is going to be, but it's also remember. So then it's going to kind of be pushing down because the electrons are pushing them down. Okay. So you use the wedge dash to kind of give us that 3D structure. Okay, and that's what it's typically for. Okay, we already talked about multiple bonds. So we know that if you're sharing one electron, if you're sharing two electrons, that's a single bond. If you're sharing 4 electrons, that's a double bond. If we're sharing 6 electrons, it's a triple bond. Okay, so when we also think about that, we can also have cases where we have more than one center atom. Okay, and I'm going to give you an example of that here in a minute. So if we have C2F4, so this guy is called tetrafluoro. In this case, carbon is going to be the center atoms, but both of the carbons are going to be the center atoms.
Dr. Henry, there's a little bit of an audio issue on my end. Half your words, like the connection is dropping, so you kind of sound like robot-y.
Okay. Was that the same thing that you guys were getting the last time? Is it better now? Or is
It sounds good. It's only happening sometimes, like 25% of the time, 30.
Okay. So a quarter of the time it's bad. Okay. That's good to know. I don't know what I can do right now. So I don't know if that is out. So we'll bear with it as much as we can. If it gets really bad, let me know. Okay. So we have the two carbons that are going to be acting as our center atoms. How many valence electrons does the carbon have? How many? Carbon has how many valence electrons? They have 4. Okay, if my pen writes, Zoom is just messing with me today. So. Okay, and then we have fluorines, right? Fluorines have how many valence electrons? 7. And this is just a hint so that you guys know, fluorine will never form a double bond. And it also will never be in the middle, unless there's hydrogens. So, a hydrogen. Okay, so 7 times 4 plus 2 times 4 . So 36 electrons. So how can we make that work? Between the carbons. Okay, so that gives all the fluorines 8 around it. So what do the 2 carbons have to do so that they reach their octet? Okay, so we get a double bond between the 2. So in this case, we look at each of the center atoms and we determine the molecular geometry of that. So what would be the molecular geometry? If we looked at the center atoms, this first carbon as one of the center atoms. How many attachments does the carbon have? How many things that is attached to it? How many different atoms is attached to this carbon?
Four connections with fluorine.
Okay, nope.
Three.
How many atoms are attached to the carbon?
5.
Atoms, not electrons.
Oh, yeah, 5.
Three.
Three.
Three. 1, 2, 3. Okay, since there are
Oh,
3 attachments, what would be the molecular geometry? Yes, trigonal what? That's right, trigonal planar. So each of the carbons are going to be trigonal planar. So its wedge diagram, since it's trigonal planar, meaning that they're all in the same plane, it's going to be real simple. All you're going to draw is C double bonded to a C, and then you're just going to have your fluorines are kicking out here. And the same thing. So it's just that.
The same plane.
Trigonal planar.
Oh, is it the planar that tells
Mhm.
us?
Yes. So there's no, it's all kind of flat. It's like a flat piece of paper. So they're all in the same plane. But we know that if it's a tetrahedral, you have stuff hanging out. Do me a favor. You have the kits in front of you. Right? Grab a kit. Okay, so we're gonna get carbons with 4 holes. Carbon with 4 holes, and then you're gonna get the green ones. The fluorines are green. They only have 1 hole, so, because they can only form 1 attachment. That's selfish. You're gonna need 4. They both should be 1. So we're also going to need the flexible arms, so the short, the longest arms. Yeah. Nope, remember, you're doing this one. So. It's not showing up. It's supposed to be plain. Okay, so if you look at the structure, it's planar. They're all in the single plane, even though our double bond is like arcing that way. So they're all in the same plane. So, planar. Okay, now if you guys can do me a favor, do methane. Chemical formula for methane is CH4. Was that? No, you can leave it, leave it together so you can compare this. Okay. So you can see the difference. This is not planar, right? They're not all in the same plane. Where's your crew? They're like,
Should have joined that program.
okay. You guys see it? Okay, so we're going to talk about molecular polarity. We've already talked about molecular polarity. We've already also talked about asymmetry, right? When we make reference to asymmetry, we're making reference to the charge distribution. So we're looking at the distribution of charges, okay? So the more electronegative atoms are, you're going to be pointing towards, the more electronegative atoms point towards the positive plane, the less electronegative atoms point towards the negative plane. In other words, the electron is going to be favoring one side or the other, right? If there's a polarity. Okay, so I'm going to show you this and I'll explain it to you. I talked to you guys about the doctor, right? Okay, so you guys all have methane in front of you right now, right? And if you guys can do me a favor, take your one that was this guy here. So what we're going to do is gonna take off the arms and then put all your greens on that one. Okay, so that's going to represent carbon tetra chloride. Okay. So if we looked at the bond polarity between carbon and chlorine, can you guys do me a favor and tell me the bond polarity between carbon and chlorine? So I'm talking about just a single bond between carbon and chlorine. How do I calculate the bond polarity? What do I use? You guys don't know, I don't know either.
Would it be 3.2 minus 2.6?
Okay,
And that would make it polar?
okay, so we use the electronegativity, right, which is, we had 3.2 minus 2.6. That would be it. That's it. 6. So we know that that's greater than 5. So that means that our molecule is polar. Okay. So that's a polar molecule. Okay. Now let's look at carbon and hydrogen. So we know that carbon is 2.6 and hydrogen is what? 2.2. That's going to equal 0.4. Okay, is that going to be polar or non-polar? Okay, so we know that in the case of methane, which is CO4, you have 4 attachments that are all hydrogens, right? So you know that the electrons are being shared evenly between those. So we know that the molecular polarity is going to be what? It's going to be non-polar because there's no pull, there's no distribution. Okay, all of them are being shared evenly, so nobody's pulling away from each other. Okay, now in the case of chlorine, now you have somebody pulling this way, you have a person that's pulling this way, you have a person that's pulling this way, and you have a person that's pulling that way. Remember when we put that person in the middle and you guys were all pulling her legs, right? And you were all pulling the same. Did she move anywhere? She didn't, right? So that's another example of being non-polar. So both of those cases, both of these cases are going to be non-polar. Right? Okay. So in the case of the methane and the carbon tetrachloride. So what happens when we remove? We do this. We put a 1 chlorine on our methane. So we replace one of the hydrogens with the chlorine. Okay. So in a situation like that, we know that chlorine is polar, right? And then the hydrogens are non-polar. So overall, what's going to happen to the molecule? That's right. We're going to form a pole, right? Because in this case, what we're saying is, you're volunteering. You're going to be this chair. I need 4 ladies. You guys get to fight over Jason. You can fight over him too. Yeah, no, come on up. You've already volunteered. Come on up. Come on. Okay, so actually, yes, let's do that. We'll have you. Okay, Jason. Let me. We'll adjust it so that we can actually see the back. Did you guys see Jeremy and Jason? Okay, any 3 ladies?
That's so far. I have to walk all the way around.
Oh, that's right, you can come to, come on. No, you're right here, you're in the first one right here, and, yes, excellent. This will work out great. Okay, you're gonna have to loosen up a little bit. Put your legs up so we can move. Okay, good. Okay, good. Okay, so you get a leg. Okay, you get a leg. And then you get an arm. Okay, so Jeremy is chlorine. You guys are hydrogen. Okay, so in this case, you guys pull. Well, you guys are pulling. So in this case, Jeremy is pulling, right? So which way is it going? Which way is the electron going? Towards
Us?
Jeremy.
Oh.
Wow. Is it? Are we going towards you?
Doing great.
It doesn't matter though, but you guys are pulling. Because you guys are weak, right? So in that case, Jeremy is the stronger, right? So the electrons are all moving towards him. So we have a molecular polarity going towards the one that has the strength, right? Electronegativity. Okay. You guys see that? Okay. So as we increase the numbers, you didn't stretch, did you? Nope. Okay. So in the case of where we have just that chlorine, so in this situation, we're forming a pole, right? We have asymmetry, okay? I'm going to show you that here. Okay, so this is this situation right here. Okay, where the yellow one here is representing chlorine, and so the overall molecular geometry is going towards that chlorine. So we form what we call a dipole moment or a net dipole. Okay, if we have two chlorines, we're going to form a net dipole between the two. If we have three, we're going to form it between the three. And if we have four, it's going to be all even, right? So that's going to be nonpolar. So nonpolar here, but if you have fours on that side, yes.
Does this only work chlorine?
No, it would have worked the same way if there was fluorine or if there's oxygen. Anything where there's going to be a pull, right? So if there's a strong enough electronegativity to make it polar for the bond, that's going to be the case. Okay, questions? Cash? Kool-Aid? Okay. So in the case of where we have carbon in the middle and we have oxygen on both sides, we're also not going to get a dipole moment because your oxygens are pulling evenly on both sides, right? So then that you're not going to get a dipole moment formed because you're pulling away. Now, in the case where we have water, we have hydrogens on the ends and we have oxygens. In that case, the moment is going towards the oxygen. And so the dipole moment is moving towards the oxygen, meaning that the oxygen has more pull than either the hydrogens. Okay, so the next thing we're going to talk about, we're going to take a 5-minute break. I will take 15-minute break, come back here, and we're going to finish up the section. It's going to be organic compounds. Nomenclature.
Dr. will be here.
Yes, get his butt up. He's on my list.
Henry, is organic chemistry harder than general chemistry? Or
It depends on the type of student you are. What do I mean by that? So if you're so a lot of bio. It's funny because a lot of bio is memorization. We're really good at bio and memorizing stuff like that. Real great at organic chemistry because there's a lot of memorization. General chemistry, a lot of calculations, a lot of math, a lot of big picture concepts. You need those things for organic chemistry, but a lot of organic chemistry is going to be a lot of memorization because you have to memorize mechanisms. And so if you're good at memorizing stuff, you're going to flash that as a sentence.
Theories that I can go through organic or the general.
Yeah.
Not sure yet. Because I'm like, okay, which
For-
one is this one gonna help with the most?
Yeah.
Intro to chem.
Intro to chem.
General.
If you decide to go general, so you just have to do general.
It's prerequisites for the PT program, so that's why I'm like, I want to go the easiest route for me so I can get the best grade.
Okay. Well, then that's 2 more classes for general.
Right.
And then you can take the intro to organic chemistry. That would just be one class.
So there's a series, like
This is a series. There's 2 weeks of this. Yeah.
right.
Yeah. Or you can do. You have options, yeah. Yeah, well, it'll be a total of 4 classes for, because you have to finish. Yeah.
Yeah, that's
And then you have.
We're on break.
So,
Yeah.
so,
Yeah, either way, it's
Where's
still
everybody
process.
at? It's a
What
break.
was that?
Where's everybody at?
Great.
The break. You have 15-minute break. Higher?
Dr. Henry,
Yes.
I had a question about the practice exam.
Yes.
Is it due on the 5th of April?
It is due on, no, it's not due on the 5th of April. Does it say it's due on the 5th of April?
It does.
I will fix that. That's right here. It said it was due on the 22nd. So I'll fix that as well. Still say the 22nd. It should say. Okay, so I'll fix it. Okay, so I'll fix it. It was supposed to be fixed.
I think you need
He wasn't there.
I
texted him.
I just kind of like
I'm sorry, when did you say it's due?
It's due the same day the exam is due, which is the second when we get back, the Wednesday when we get back, which is the 12th.
Okay. Okay, thank you.
It's the same day the exam is.
Wait, is your close to the exam?
Yeah, the exam is every day, so okay, so you'll have.
Yeah, what? No way, stop, stop.
Hey, Dr. Henry,
Yes,
our exam is due this Friday, yeah?
no, but if you want to turn it in this Friday, you can.
Wait, when is it due?
It's due the Wednesday when you come back.
Oh, you changed your mind? Sorry, I can't hear you. Your audio is really bugging out.
Okay, I said, yes, I changed my mind.
Thank you for changing your mind.
You're welcome.
You've restored my faith in humanity.
But that also means that I have higher expectations of you guys.
Coward bought, even somewhere.
Thank God, Dr. Henry. You really did cheer my day up.
Okay. Are you guys ready?
oh, no.
A few more minutes. Did the review help?
Nerd
It's
stuff.
geeks, geeks, yeah, because they're not smart, I'm not smart.
Oh my god.
I'm a geek, bro. You're gonna title me right.
So over break, there will be a couple of reviews, so I'll let you guys know what they are. Yes,
Are you still having cocktail hours over spring break? You don't have to. I know you're not off the clock here.
at the first Sunday of that. Yeah, not this Sunday, I am not doing it this Sunday,
No, you're
sorry, yes. But the Sunday after that, Sunday,
And we could go back, it's not Monday, that Monday
Yeah.
morning.
no, that Sunday before,
No, yeah, I'm just tracking, so that's okay.
yeah, because
It's a plant-based iced tea, even though tea's already plant.
it's really good. It's really good, yeah.
It's still pressed. Let me see it, let me see it. Let me see it. Oh, Lord.
I like it. It's like refreshing. Very refreshing.
Okay.
And it gives me
So I'm gonna go for it.
Okay, so the jam is due April 4th. And cocktail hour will be Sunday, the 9th,
The ninth?
April 9th.
Henry, when I try to join the cocktail hour or like
Okay,
the
cool.
Zoom, they're so hard to find on campus. Like literally.
If you do me a favor, go to modules.
Yep.
There it says important links, modules, important links.
That's why. So I found it once and I tried looking for it again. I was like,
That's where it's at.
Oh my god,
you're lying.
33 grams.
Oh, okay.
That's right. But then 33 grams of more sugar. That's a catch, bro.
Okay, but it's under modules and important links.
I want to say 16 now.
That's a lot.
Yeah, it is. That's hella sugar, bro.
Might as well better off eating like.
I ate really
cupcake.
good today. Really good. Had eggs and sourdough,
What?
and then I had
On
chicken
sourdough?
stew.
What? Oh, Dr. Henry, you know anything about the human anatomy?
I do.
So, like, you know anything about when it comes to like physical stuff, like squat form and all that?
Yes.
So why do like when people squat have a hip shift when they squat? Does that make sense? When they shut, when they're squatting, like, shift the center of the
Yes. Yes. Yeah.
Is it like an imbalance? Like a,
Yeah,
like a knee problem
so
or-
typically, yeah, so it will result that an imbalance in terms of either form
Okay,
or like there could be like damage to one knee, so they're favoring. So typically you naturally favor one side or the other.
okay.
So, yeah. So yeah, there is a bias, yes,
Okay,
because there's a bias.
got it.
And then, like, do you know?
I had to sit there and think about it because I just.
Oh, but no weight, no, I'm cool with no
Okay,
weight.
see, then.
So do you have a hip shift when you squat?
I don't know, I used to have a big one, but I do like a lot of Spanish squats and a lot of down work in my knees,
Uh-huh.
but it's still there, like, it's not a small thing, it's not a big thing. I think like, I do RDLs, yeah, like I do like bench, what do you call it, Bulgarian squats, I do Bulgarian squats, single leg, yeah. For real? Damn, because I went to physical therapy for 2 years for my knee.
And then, like, if you're having like Bulgarian bias in a certain way. Shift that way.
That's not, are you serious?
Fix that problem. Then you can get some like hip problems.
So you're just causing damage to yourself later on. Much
No
more.
way, I'm feeling it in my back right now.
Yes, exactly.
You know what?
Okay, organic chemistry. So let's look at the definition of organic chemistry. So often we will talk about organic, something is organic. Oh, it's organic, it's organic. So what organic basically means is that it has carbon. Okay, so organic molecules are molecules that have carbon in it. Now, there has been a long debate between organic chemists and inorganic chemists. Organic chemist says that anything, initially they said that anything that had carbon in it was considered to be organic. Inorganic chemist says, no, you can't take all of carbon. Carbon belongs to us too. So if it has carbonate, cyanide, oxide with carbon, that would have one carbon or something like that, a couple of oxide. So those guys are going to be called inorganic. So if you have the carbonate ion, which is CO what? CO what? carbonate. Anyone? Anyone?
CO2.
Not CO2, that's carbon dioxide. And that's considered to be, quote, inorganic.
Oh, God.
So carbonate.
CO3 -2.
That's right. CO2 -2. So carbonates, so those are going to be considered to be inorganic. Okay. Now, but if you have anything that just has carbon and hydrogen, that's going to be considered to be organic. Not only that, it's also going to be called carbon. I can't remember. Hydrocarbons. There we go. Yes, I do need to sleep. Hydrocarbons. It's one of those days. Okay. So hydrocarbons have only hydrogen and carbon.
Hydrocarbons are organic.
That's right. And then also,
Wait, they're both
no, they're organic.
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 It has an H.
They're not inorganic.
So you said anything that with carbon dioxide is inorganic.
If it has one carbon and one oxygen, or one carbon and two oxygens, all of those are going to be
So one
inorganic.
carbon,
So carbon dioxide.
carbon, two
Okay. So the inorganic guys like to claim. Okay, so hydrocarbons, there are three types of hydrocarbons. We have alkanes, alkenes, and alkynes. Alkanes are going to be single bonded. They're also going to be called saturated hydrocarbons. So they only have single bonds between the carbons. And I'll show you an example here in a minute. Alkenes are going to be unsaturated. What we mean by saturated basically means that you put in so many hydrogens that you only have single bonds. So if it's saturated, you have only single bonds, okay? If it's unsaturated, that means that you have at least one double bond, okay? And then you have, so alkenes are gonna have at least one double bond. Alkyne, they're gonna also be considered unsaturated, but they're gonna have at least one triple bond, okay? So I'm gonna give you guys some tips on nomenclature here. Of organic compounds. We have meth. We have F. We have pro. We have het. We have hex. Het. Oct. Done. Deck. Undeck. Dodeck. Trideck. Maybe ask me about this later. I'm gonna rip you apart. I promise you. There's no going home. We go home when we're done. I figure an extra hour.
Let this professor talk to him. Gone
Ripping
crazy. of
people
being
apart.
angry. Refuse to go home.
Okay. So for organic compounds, when we're talking about organic chemistry, when you have one carbon, it's going to be methane, right? Methane means that everything is a single bond, it's saturated. Methane. So we use ANE. Okay, so methane, and we know that methane is one carbon. It has one carbon and it's CH4. Okay. Ethane is going to be C2, H3, H6. Okay, so what's going to look like, it's going to look carbons attached. Okay, so we know that carbon can hold 4 things. It can be attached to 4 things, right? So if it's totally saturated, you're going to have 3 hydrogens, and it's also going to be attached to another carbon. Okay, so that would be ethane. Okay, so if it's A and E, it's always going to be single bonds. Everything in there is going to be single bonds, and so you're going to use the hydrogens to balance out, so that you have 4 attachments on every carbon. Okay, so this here, this here is our Lewis structure, but we call this the expanded structure. So you can see everything, right? So we also have a condensed structure. Condensed structure would be okay. So in this case, it's the same thing, but it's condensed. We're just showing the bond here is representing the bond between the 2 carbons. Okay, so that would be the condensed structure. So when you're looking at organic compounds, you're going to see the other way that you can show it is it's called the skeletal structure. In the skeletal structure, each point represents a carbon. So this would be 1 carbon, that would be 2 carbons. Okay, this is the most common way that we show it because carbon structures are typically very big and very obnoxious looking, right? And so if you have all these carbons, you get tired of writing C, H, C. So you know that there's a carbon there, and you know from your experience that carbon has 4 attachments. So you know that there has to be 3 hydrogens here to balance it out, okay? And then there has to be 3 hydrogens here as well. So these are 3 different ways of 4 different ways of showing us the same. Okay, so this is the skeletal structure. Type it out for you.
So just the line is the skeleton?
Just the skeletal, yes, just the line. Where each point represents a carbon, so each N represents a carbon. Okay. This here, this here is the condensed. Structure. And this here is the expanded structure. Okay. Questions so far? No questions, okay? So for our purposes and for time purposes, I prefer the skeletal structure because it's easy for me to see and it's easy for me to count. So can I go ahead and erase this so that we can start showing you, I can show you how to use the skeletal structure. Let me know if you guys got it down. You need a little more time. Okay. Okay, everybody got it down? Now, it's important that you understand these prefixes, right? Because these prefixes are going to be used throughout all of organic chemistry. So when you're talking about alcohols, when you're talking about ketones, when you're talking about, and so you need to be able to understand what you're talking about, how many carbons are going to be there, right? And this is going to be the foundation of organic chemistry, is understanding the name. Okay, so pay attention. Okay, so each point represents a carbon. So how many carbons do I have here? Yep. I have 3 points. I have 1, 2, 3. And you want to get in the habit of counting your carbons. Remember this so that you know which carbon we're talking about, because we're going to have chains coming off these carbons at some point too. Okay. So here, this is a 3-carbon, and it's all single bonds. Okay. So the name of this carbon would be what?
C3.
Okay. No, that would be its chemical formula, but you haven't forgotten it. Nope. What? Say the name. Very good. So the name of the carbon will be propane. Now, if we wanted the chemical formula of the carbon, we know at the end of each of the carbons of this structure, they can hold 3 hydrogens. If it's in between the 2, it can only hold 2 hydrogens. So you would count up all of the hydrogens. So you have C3, there's 3 here, there's 3 here, and there's 2 here on the center point. So 3 plus 3 plus 2. That's 3 plus 3 plus 2. 8. Okay. So you guys can see it. I'm going to do an expanded way 1 time. This is it, 1 time. Okay, so okay, so this center carbon represents the number 2, right? It's going to have 2 hydrogens on it. But you know that hydrogen can have 4 attachments, right? It's going to have 4 attachments there. So that's 1, 2, 3, 4. This carbon is going to have 3 hydrogens. Okay, now if we count all of our hydrogens, that's 1, 2, 3, 4, 5, 6, 7, 8. Okay.
So how do you know this? Oh, propane because prop is 3.
The A represents all single bonds. I said that the first time. A and E means single bonds. Okay, actually I said it.
Oh, alkane single bonds.
That's right. Yes, alkenes, double bonds, and alkynes, triple bond. Yeah. Okay.
And then we got the pro from the
Yes,
okay.
propane, 3. There's 3 carbons. So we have propane. So ethane has how many carbons? Ethane
That's 2.
has 2. octane has how many? 8. Okay, so what I want you guys to do is on your paper, draw me octane. And you have your options. You could draw it the long way. Actually, I want you to draw it the long way, and I want you to draw it the short way. Skeletal structure.
You said draw octane?
Yes, draw octane, the expanded structure, and then also the skeletal structure.
Would it be
then-
oh,
what was that?
I was just gonna double check. Would it be 6,8H20?
No, you would. It's always the. You're talking about the chemical formula.
Yeah, so like I did the lines and that's how much hydrogen I got.
How many carbons do you have for octane?
8.
8. Okay, so it's C8. Is that what you said?
Yeah.
I thought you said 6,8. I was like, what is 6,8?
No, I said C8H20.
It's a C8H20. So 6 times 2 would be 12 plus 2 times 6. I mean 2 times 3, which is 6. So 12 plus 6, so that'd be 18.
Oh, okay. I'm just basing it off the skeletal structure that I drew.
Okay. So you may want to take a relook at your skeletal structure because you have 2 too many.
Okay.
Okay, so when the skeletal comes together to form a point,
That's a carbon. No, it represents 1 carbon.
okay, 1 carbon at the point, and
No, you're saying hydrogens. Okay, so if you look what I drew, right?
Yes.
Take a look what I drew. Okay, so it was for propane, it was just a hat, right? Okay, that's 3 carbons. So each point represents a carbon.
1.
That's right. Now, where there's a point coming together with 2 lines, right? So that is where we're gonna have 2 hydrogens in addition to that 1 carbon. That's gonna be attached. Okay, so look at the figure and then look at the expanded structure and the.
Okay, I think I got it.
Okay.
Dr. Henry, can I draw what I drew on my paper?
Yes, you can.
Just to double check because I'm not understanding.
Sure.
How do I? This is a 2 right here. I don't know if I'm doing it right. It's a 5. That's a 6, 7, and an 8.
That is correct.
Okay, so you have 3 here, 3 here, 3 here, and 3 here.
No,
Hydrogen? Okay.
remember, where there are 2 points meeting, you're only gonna have 2 hydrogens.
Okay, so you have 3 here,
We have both ends.
and then you have 2 here,
Yep, 2 there.
and then is this a point meeting?
Yeah. the ones at the bottom. Yes. So anything in the center, only thing that's gonna have 3 are gonna be your ends.
Oh, okay.
And then draw it out, and then I want you to draw it expanded, where you actually draw all of the carbons and then put all of the hydrogens on.
So it's gonna be like, there's gonna be a total of 8 points.
There's gonna be a total of,
Like
there's,
8 points, like
That's right.
point.
yeah,
Okay.
well, 8,
Carbons.
yes, 8 points where you start, your first one is a point, The next one is, yes, that's right.
Okay.
Okay, I get it.
You get it?
Yeah, I wasn't counting the correct way.
Okay. So. Okay. So that's 1, that's 2, that's 3, that's 4, that's 5, that's 6, that's 7, that's 8. Okay. Now, when we expand it out so you can actually see everything. This is my first card. This is my second card. Second card is going to have 2. This is my third card. 4th. 5th. 6th. 7th. And 8. One, two, three, 4, 5, 6, 7, 8. Okay, so the ends have 3 carbons. Everything in the middle are going to have 2 because carbon can only have 4 attachments. Okay, and if everything is single bonds, you're not going to have any double bonds in this situation, right? Because it's an AME, that means there's only single bonds. Okay. Okay, so okay. So when we have a double bond, just one double bond, yeah, just one double bond, what we do is okay. So when there's a double bond, 4, 5, 6, 7, 8. Okay, we have one double bond here, right? So instead of calling it alkane or octane, we're going to call it octene. Okay, so in this case, this guy would be called octene. But we have to say where the double bond is at. Now, the way you determine where the double bond is at is by counting. This here is 1. This is our 1 carbon. This is 2. This is 3. This is 4. This is 5. This is 6. This is 7. This is 8. You want to give it so it has the lowest number possible. You can count from either direction, but you always want to make sure it has the lowest number possible. If we counted it from the other direction,
So wait, how do you terminate it? I apologize. I didn't understand.
1, 2, 3, 4, 5. Okay, so again, you want to count and you want to have the lowest number possible. Okay, so which is lower? Where the double bond is at. Here we have it between the 3 and the 4, right? And then here we have it between the 5 and the 6. What number is lower? Between the 3 and the 4. So what we do is say where the double bond starts at. Where does it start at?
The 3.
So then we would say 3 octene. Okay, so that tells us that the double bond is at the 3rd carbon. Okay.
Is this the same for triple?
Yes, this will be the same thing for triple. So you would tell me where the triple bond is at. Yes. So if it was 3 octi, then you would have the triple bond. Okay, and I'll show you that here in a second. Okay. So another way of doing it is you can also say so this would be another way of doing it. So you could put it right next to the root, okay, or the suffix, right? So to tell me where it's at. And typically it's done like this if there's other structures that have that. Okay, so we'll talk about that in a minute. Okay. Oh, we haven't even got to the hard part yet.
I'm not surprised.
This ain't the hard part?
No, this is not the hard part.
So you count, so in order to find 3 octene, you have to go with the lowest point.
The lowest number.
So you count the top, the bottom, and the top.
So
you-
yeah, so you want
always
to find out where that structure's at.
Okay.
At the lowest number. You always want to use the lowest number. You want to be number 1, right? You want to always do the lowest
And then
number.
how do we get that double bond? Right, 13.
How do we get to that number? I just put it.
Okay.
So, and that would happen by a chemical reaction.
Okay.
Okay, so let's say the double bond was on the second to last single bond, or second to last, we would pick 1 or 2.
So you're saying if the double bond was here instead of here, so we'll put this one back on. So you're saying. Okay, so then put a 1.
Oh, you go for the lowest.
Always go for the lowest one. Yes. So you always want to have the lowest number possible for your structures. And it's always going to be based upon who has priority. We'll talk about that in a minute.
So
once I
on
start to do
the
this.
bottom, you count left to right, and the top you count right to left.
You can count any way you want to. You know, you only, but you have to start at 1 in, right? So 1. But the thing is that you always want to. So here I counted from this part because this will give me my lowest number, right? It gives me my structure at the lowest number. Now, a double bond is more important than a single bond. Right? Okay. And then a triple bond, technically, a double bond and a triple bond are about equivalent, but typically you want to end it with a triple bond.
So does that mean you count for the double bond?
No, you always count from the end. You always have to start at the end of the cartridge. Okay, so you start at this end or you start at that. Okay, you need some type of direction, but it doesn't matter. You start at 1 end, but you always want to end up with the lowest number. So that's kind of count from both sides to find out where that lowest number was. Don't make it harder than what it is. It's not that hard. It's just counting. Right? All you gotta do is count. Okay.
Dr. Henry,
Yes.
if it was in the middle, like from 4 to 5, where in both cases you count it's 4, it's just 4.
Doesn't matter. Then it's just 4. Yeah.
Okay.
Okay. Okay, so let's do single bond. Okay, so let's do decade. Okay, and this time I only want you to do the skeletal structure. And have you guys realized what is the benefit of using the skeletal structure? Nobody?
Faster.
It's faster, right? You don't have to worry about all the damn hydrogens. That's good. Did she send it to me?
Yeah. It's, everything is on the.
No, I want the structure, not the name. Structure.
Yeah, I did the structure.
Okay. You're giving me the name too.
What's that? You're cutting off.
I said you were giving me the chemical formula.
Yeah, I was just that's how I was double checking my structure.
Okay, you guys ready? So you guys tell me what I'm doing, okay? So starting here. That's what? 1, 2, 3, 4,
5, 6, 7, 8.
That's it. Okay. So if we're going with the formula. 1, 2, 3, 4, 5, 6, 7, 8. 8 times 2 plus 6. So you have 3 here and 3 here. Right? 16 plus 6.
Yes. So how'd you get the 8 times 2 plus 6?
Because the ends always have 2. The metals always have 2. Everything in the metals always gonna have 2. It's all single bonds. And it's that K means that they're all single bonds.
The ends ones have 3, and then
The middle ones are always gonna have 2, but they're all single bonds. So now I want you to write, let's do three empty. Three empty. I want you to draw 3 empty. And the way that you would do a double bond, just so you guys know, in the skeletal structure, so it's the double bond. Lines, double bond, that's how you represent double. So one, 5, 6, 7. 1, 2, 3 on the third segment. That's where that starts. So you want to empty. Okay, when there's a double bond, you're only going to have one hydrogen attached to each of the carbon where the double bonds are at. So if we're counting, this guy would have 3. And then this has 2, this has 2, this has 2. And then these two have 1 plus 2. So then that gives me my total 7, 6. H 14. Yeah. That's
Wait, Dr. Henry, how do you decide what double bond?
the double bond. I'll go to the process again. So the double bond is given to us by the number. It tells us where the double bond is starting. Okay. So we draw our structure. 1, 2, 3, 4, 5, 6, 7. We have our 7. We put double bond where the 7. 3 and the 4. Okay. So the way that you get your chemical formula is 7 because it's F, right? That means 7 carbons. And then at the end, each end has how many carbons? 3. So how many ends do we have? There's 2 ends, so 3 times 2. All right. 3 times 2 is going to be 6. Okay, because that's the end. Right there, so that's 1, 2, 3 points, right? So how many are going to be at each of those points? 2. Okay, so 3 times 2, that's also 6. And then where the double bonds are at, there's going to be how many carbons? I mean, how many hydrogens? 1 in each one, right? So 1 times 2, that's 2. So that's a total of 14. Yes, because there's 2 here, there's 2 here, and there's 2 here.
And then for the first one,
The ends, remember? 3 here and 3 here. There's 3 at each end. 3 here, 3 here.
so then one would have 3 times 2. Or a whole.
3 times 2 because you have 2 ends. 1, 2, right? And then you have, right, let me do it like this to make it a little easier. 2 times 3. That's better? Don't overthink it, right? Don't overthink it. If worst case scenario, draw it all out, right? If you need to draw it all out, you know that there's how many things can be attached to carbon? 4. Okay. So either if there's 2 double bonds, let's draw this one out, just so you guys see it. So we have carbon, 1, 2, and then our second one, and then our third one, You got third, then fourth, there's a double bond. Okay. This, okay. So that's one, this is our first carbon, second, third, fourth, fifth, sixth, and seventh. Okay, so that's all seven, right? 7 carbons, right? 1, 2, 3, 4, 5, 6, 7. Okay. Now this one, it has to have 4 things attached to it. Okay? There's a hydrogen here. There's a hydrogen here. Okay. Here, there's 2 right here. So then how many hydrogens do I have here? 2. I have 2. Now on the third one, this is 1, 2, 3. So I have to have one more hydrogen. And then on this one, there's 1, 2, 3. That means I have to have 1 hydrogen. Then this one here, there's 1, 2 right here. So and then this one. So this structure means exactly the same thing that we have here. Okay. And so, but this one saves us a lot more time. You know, and then when you start to talk about chains that are 27 long, 32 long. So you don't want to sit there and have to write down all of those targets. Okay.
Dr. Henry, you're kind of cutting out, but I understand pretty much everything from the skeletal in terms of adding up. Besides, like the double bond from 3 to 4, each line becomes 1 hydrogen.
Yes.
Okay. And then if you were to have a triple, it would be 3 there, that right? Like 3 hydrogen.
We'd have not 3 hydrogens. If we had a triple there, we would not have any hydrogens.
Oh, I see. Okay.
So remember, right here where there's a double bond, that's a hydrogen. These guys are attached to the carbon. So that's 1, 2, 3, 4 things that are attached. So the double bond in this case is attached to the back, right? So there's 2 lines there.
Yeah, I see. I see it.
Okay, so you have to think about it. Stress regular structure is that having 8 around it. That's all it is. Okay. Okay, how are you guys doing? You ready for it to get a little bit harder? Down over here. Excellent. That's good. I'm glad that you guys are ready. Okay, so sometimes we may end up having more than 1 double bond. So we have multiple double bonds. The way that we start doing that is these are the 3 things that we learned earlier, right? Remember mono, di, remember those? Know what? We get that era, right? So let's say we have a double bond here. So in other words, now using the same structure, we have a double bond between that first carbon and the second carbon. Okay. Okay, so the way that we would do this is, this name of the structure would be called 1, 3, F, the di, E. Okay, di meaning for 2. That's 2 means di means 2, right? Okay, hepta, di. Okay, 1, 3, hepta, di. Okay, this is one way of doing it. The other way of doing it is call it 1, 3.
For those dashes between capital and one?
Yeah.
Okay.
Okay, so if you guys look at the back of your shampoo bottles or your detergent, you'll see a lot of these things. So if we had 3 double bonds, if we had 3 double bonds, what would this compound be called?
One, oh wait, right? Or no? It'd be one, hepta. No, I'm sorry.
No, don't stop. Keep on trying.
One,
Look at what we just did and try to apply what we just did to.
3?
1, 3, okay.
Oh, shoot. I don't know.
And then what's next?
It's 1, 3, 5. Hepatriene.
Hepta. Right. Because there's 3. 1, 2, 3 double bonds. So we call it trying, right? Keep trying. Get back to it.
I'm trying.
Hepta. 1, 3.
okay. So why is there a 5 in it?
There we go. Good job. Okay, where's the other double bond? Where does it start? At the 5th carbon. So you're telling me the location of each of the structures that we have. That's it.
Oh, okay.
Okay, so I'm gonna put a structure up, I'm gonna put a name up here. Okay, guys ready? Okay. I'm gonna erase this.
Dr. Henry, quick question. For the double bond, you put hepadiene. Was that misspelled and it was supposed to be heptadiene?
It just said hepta.
Oh, okay.
Did I forget the A?
Yeah, you didn't put the T. You put hepa.
Oh, sorry. There should have been a T here, my bad. Yeah, that was my bad. Okay, let's. first thing that I want to do, I should do what?
The points.
I should count the points. So which side should I start on?
Left.
And why the left?
Because of the double bond is closer to that one.
Okay. Good. You guys get that? Yes. Okay. Okay. Let me give you my name.
Would it be 2, 4, 6, 7? Un deca tetraene.
There's 11. It's 11 carbons, right?
So Ude.
Wait, is it gonna be 7 or is it gonna be?
Deca. Tetra.
Yes.
Tetra. Okay.
I'm trying to give you that color. Oh, I understand.
Okay. Because there's 11 carbons. Okay. Double bonds were at 2, they were at 4, they were at 6, and at 7. So it started at 2, the 4, the 6, and then also at 7. Okay. Okay. And then that means that there's 4 double bonds. So that's the tetra.
So the tetras from the other 3.
No, the tetra, because how many numbers do you have? So that's 4. So that tells me how many double bonds I have. It tells me where they're located.
Oh, okay, I'm tracking. All right.
Okay. So we're going to work backwards. So this time I'm going to give you the name, and you guys are going to give the instruction. Okay. still working on finishing lunch. So. Hey guys, ready? Okay. One, three, seven, no, try. What am I gonna do?
Start.
How many points?
Skeleton. The skeleton. 9.
9. 1,
2, 3, 4, 5, 6, 7, 8, 9.
Okay.
And then double bond goes to 1 to the 2.
Okay.
And then it goes 2 to the 3. And then no, 3 to the 4. Sorry, 3 to the 4.
Okay.
And then it goes, other bond goes 8 to the 7.
Okay, so this will be okay. Does it look like that?
Yes.
Okay. Okay, so you guys good so far?
How would you do the chemical formula for that? So it'd be C9.
Sure. So we have C9. How many we have here?
So it'd be 2 now.
How many we have here?
I want to say 4, but it's not. I think it's 2 as well, right? It should be 1.
Should be 1. Yep. Let's look at how many lines are connected. That 1, 2, 3 lines that are connected at this point, right?
Oh, correct.
So that means that there's only 1 left. Okay, and here. 3 lines. So there's 3 lines connecting. So then how many? 1. 1.
Two.
How many lines are connected?
Oh. 3.
There are 3 lines, so then I have how many left? 1. Okay. And then here, how many lines are connecting? You have a line coming this way, and a line coming this way. How many lines are connected? Okay, so then that means I have how many left?
1. I'm trying to understand it.
Remember, you can always have 4.
Okay.
4. We're going to 4. So you look at the lines that are connected, right? So let's go back over. Here, we had 2 lines connected. So then how many are left?
1.
You can have 4.
So 2.
Okay, so 4. 4 is the last number. Okay, 4 is the last number.
All right.
Okay, so we have 2 lines here, right?
Right.
So then how many do we have left? 2. Okay, so that's what we said. Okay.
Okay.
We have 2 lines here. And how many left? 1.
Oh, all the other 4.
There's altogether 3. 3. So 1, 2, 3. Count the lines. All right. 1, 2, 3. Okay. Then that means how many's left? 1. Okay. And then here I have 1, 2, 3. How many's left?
1.
1. So man, how many do I have here? 3. Okay. So then how many's left? Okay. And then here I have. And then here.
That's what I was doing. That's what I'm doing.
Okay, and then here.
That's gonna be 1.
Okay, you mean we have 1 left, right?
Yes, 1 left. 1 left.
You gotta tell me what's left.
Okay. So
Okay, so then here.
you have 3 lines that's gonna have to be 1.
Okay. And then here. How many lines do I have? Okay, so add that all together. Okay. So C9, 8, 14.
Okay.
Okay.
Got it.
Okay. How you guys doing? Ready for the next layer? It always gets better.
Okay, I get it now.
Okay. So. Alkanes at the bottom. Okay, so that means they have the least priority, right? Meaning that when we look at their last name, it's alkene, okay? And then our next one is alkene, and alkyne. These are gonna be- I don't know why. I always think triple bond should be better. But that's common. Okay. Now we're going to talk about the triple bond. Okay. And then we'll add on the double bond. So because it's a triple bond, instead of doing that, you just go like up, down, up, down, up, down. Right? Triple bonds, you can't do that because they're going to form linear structures. So, yeah. So we're going to treat these exactly the same way that we treat our other ones. We're going to count them. Okay. We also want to have the lowest number, right? So which one is going to give us our lowest number?
I just got this.
All right, hold on. This is the triple.
Thanks.
This is a triple bond, and this we have two triple bonds. Okay. So we want to count them, and then the direction that gives us the lowest number, right? So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Ooh, that's close. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7. 10, 11, 12. Okay. So we have the blue numbers and the green numbers. Okay, for you, the top or the bottom numbers. So which is going to give me the lowest numbers?
The left side.
Okay, the top or the bottom numbers?
The bottom numbers.
The bottom numbers. Okay, bottom numbers are going to give me the lowest numbers. Okay, so tell me where my triple bonds are. So we have 2, and then you said the other one starts at 9. 9. Okay. And then how many do we have?
2.
We have a total of 2. So we're going to call this guy, the prefix would be what?
Sorry.
The prefix will be what?
Oh.
Trideca or tridec.
And then How many double bonds do we have?
Two.
We have two, so what would be the prefix for that?
Die.
Di. Di. Okay, so it'll be 2,9 tridecadiene. What does the triple bond say? At the 2, right? And the other one starts at the. Okay.
So hold on, so how did you get it diamide all the time?
1, 2,
That's the two triple bonds?
di, right?
Uh-huh.
And then Y-N-E, triple bond. Okay, remember, single bond is A-N-E, double bond is E-N-E, triple bond is Y-N-E. If you think about it, A is the first letter of the alphabet, E is somewhere in the middle, and Y is towards the end, right? So your single bond first, right? Your double bond somewhere in the middle,
Right.
and then your Y-N-E, that's gonna be at the end, right? Okay. Okay, so how you guys doing so far?
I understand it. I don't understand the counting.
What do you mean by you don't understand the count? Because you have
To
the
get that.
you have the option of counting from either end. You wanna
No, no,
get-
no, 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 not that counting. To get your hydrogen for the formula.
Okay, so let's talk about the chemical formula again. Okay, so
It's because you're breaking up a lot, so it's very hard to hear you.
okay, I'm sorry, I don't know what to tell you. I have to recording the fireball up so that you guys can take a look at that one. So it'll have a better recording.
Just my mic.
Well, it's still, yeah, it has to go with our system.
Oh, really? Yeah. You can't Bluetooth it?
I guess we could try.
There's some mics that like it's on the shirt. for
Yeah.
Like $20 anymore. You Bluetooth it.
But is that gonna help you right now? So-
Yeah. Okay, my fault.
So tell me if you can hear me, yeah, then I'll repeat it, and hopefully we'll get a good recording somewhere. Okay, so the way to look at it is by counting lines. You count the lines that are merging. And for carbon, carbon can have 4 lines. Okay, 4 lines. That's the max it can have. Okay, now if you don't have enough lines, you have to add hydrogens. Okay, so we know that this is going to be C. This is going to be C what?
13.
Okay, so we're going to start at the first carbon. How many hydrogens do we have there? How
So
many?
that's 3.
It's 3. Okay, so we have 3 plus. At the second carbon, we have 1, 2, 3, 4 lines. So what do we have there? There we go.
None.
We'll have 0, right? Because you have 1 line here, you have 2, 3, 4. So that means that you have no room for anything. You got 1 over here, right? You have 2, 3, 4.
Oh, so you need to count the.
That's counting the lines, right?
Right.
Yeah. So
Oh,
technically, even though
okay.
that, yes.
I'm trying. Okay.
Okay, so on the third carbon, we're at the third carbon right now. How many lines do we have that are connected? So technically, this is a connecting line.
So 4.
So we have 4. 1, 2, 3, 4. Right? We don't have room for anything else. Okay, on the fourth carbon, how many lines do we have connected? There's one coming this way, one coming that way. So 2. That's 2. So then how many do we have left? 2. Okay. So fifth carbon, we have 2 lines coming together.
So we have 2 left.
We have 2 left. Sixth carbon.
You have 2.
2. Alexis, can you hear me?
Yeah.
Sixth carbon. On the 7th carbon. Got 2 left. 7th carbon, right here.
Yeah, you have one from 7 and one to 8, so that's you have 2 left.
Okay, so I have 2 left. Then on the 8th carbon,
So you have one from 8 to 9.
okay,
So that's 2, right?
okay. And then on my 9th carbon,
So from here you go from 9 to 10. And then you have another one, so that adds up for 2 lines, right? So you have 0.
okay, and then number 10,
Is it 2?
there's 1, 2. Here's 10 right here. This is what we're looking at right there. See circle?
Yeah.
Okay, so then that's 1, 2, 3 lines right here from the triple bond, and we got 1.
Oh, yeah. Oh, and then the 4th that connects to the 11th, so 0?
That's right.
Oh.
And then
And 2.
And then 12.
Real quick question for 11. Point that says. That the one from here and here.
That's right.
Okay,
Okay, number 12.
it's gonna be 2 as well.
From 12 to 13, that's 2.
Okay. And number 13.
It closes at 3.
Okay. So add those all together.
$20? I'm not sure.
So 8, right. So you got 8.
That's
2, 4, 6, 8, 10. Oh, okay.
okay. So how you doing? Okay, we're gonna add another layer. You ready for the next layer?
Okay, thanks, Josh. Real quick, I don't want to skip nothing.
Yeah.
Real quick.
Go to the bathroom. Quick 5-minute break, bathroom break, and then we'll come back and I'll add this next layer. And then we're gonna move on to the next functional group. Actually, the next layer. Next function. What's that, bad news? You're shaking your head like.
I was just watching a video of a woman throwing herself in like the ball pit and couldn't get out.
Where's my laptop? Forgot it.
Dr. Henry, can I ask you a question while annotating?
Sure.
It won't let me annotate.
Oh, let me stop sharing my screen.
Oh, I was gonna annotate on your screen.
Sorry, it won't let you annotate. I'm sorry about that because it's.
Oh, I see.
I can put a whiteboard up.
And then, Doctor, do you think we can do another small one, like a small example?
Yeah.
For like what the board has.
Okay, so you can annotate on my screen now.
All right, let me see. I'm just gonna replicate like what we had.
Okay.
All right, this is all I need. Okay. So here, that's 3, right?
Yes, at the end.
Okay. Okay.
Because you're saying the way that you have it drawn, do you mind if I draw it a little more clear?
Yeah.
I'm not trying to knock your drawing, but it's worse than my 3rd grade handwriting, you know, so.
Oh, you're using lines though. Look at you.
See, hey, this. All right. Okay. Is that better?
Yeah.
How about you drawing? Okay, and then you have this one as labeled as 1, 2, 3, 4. So you're
All
saying,
right. Yeah, so I'll just use dots to understand the addition. So like right here, right?
Yeah.
That's 3.
That's 3, yes.
Okay. And then you got to assume that from here to here there's 2 points, right?
Yes.
So that would be 2.
No. You're assuming, because literally this is what it is. You have C, triple bond, and then on this side you have a single one.
Oh, okay. I was trying to.
This side, and then there's one that's coming into it.
Oh, I see. Yeah. So you have 1, 2. So it's 1 right here, right? And then it's 2, 3, and then 4, right?
Yeah, that's right.
So then that turns this to 0. I'm just trying to like review what you explained, but seeing it with dots, because that's how you see it, right?
Yeah.
Okay, so you got 1, and then that gives you the 3, and then you got 1 point, 2 points, 3 points, 4 points, so you don't have room for anything, so that gives you 0. Now my question was from here, from 2 to 3, you count here 1, 2, 3, and then 4.
That's right.
I got you. I got it now. Thanks.
So you can get that, so just refill it. I'm gonna finish that.
Oh, real quick. So then from 3, it's 1, and then 2, and that's it.
Yeah.
So that'll be plus 2.
Yeah. So literally, when you're looking at that 4th point, you have this line coming in. The way I look at it is, you have the bonds that's coming from. The bond that's coming from here, and you have the bond that's coming from here, right? And that's how you make that thing.
Okay.
Okay, where here you have triple bond, triple bond, triple bond, triple, the thing back is the triple bond, right? So then you have 3 lines coming in. Won't let me draw. Too close together. So I have my 3 lines coming in here. And then I have my other one that's right here. So those are 1, 2, 3, 4 bonds.
Mm-hmm.
Okay, so I like to look at them as the minimum. So then that way it helps you keep track of the number of lines that are there. So you know that there's no more room for a hydrogen.
Right.
Okay.
Okay. So from 3 to 4, it was plus 2, right?
Yep. So
And then from 4 to 5, it's plus 2 as well.
no, because if we have a 5 at the end, that means that what's.
No. I meant like it keeps going.
Oh yeah. Okay. So
Yeah.
Or the one that we did was kept.
Yeah, basically, yeah. I just wanted to understand this merge right here.
Okay.
Right. I got you. Thank you so much. That was very helpful.
You're welcome. I'm just gonna take that. Okay, I'll see you. I'll see you. Hey, I'll try to get you.
Yeah, that would be nice.
Yeah, I'll come over.
Please.
Yeah. I'll bring dinner or something like that.
Don't leave the party over the whole weekend. Working, I hope. There's one night that is past over. I don't remember. Yes, it's been touched.
Okay, sounds good.
I have a nephew living with me.
Temporarily.
For a few months. So I'm practicing driving my car. No.
Okay, I'll see you. Okay, so you guys ready for the next part?
Yes.
Okay, I'm gonna go back to the board.
Start everyone.
What happens when we have double bonds, triple bonds on the same?
Sorry, say one
I said, what happens when we have double bonds and triple bonds on the same compound?
Bonds
And triple bonds.
Cancel out.
Two names.
Sort of, it is gonna sort of be two names. Okay, so again, you want to go with the red spectrum. Double bonds and triple bonds are going to be considered to be equals, right? But you just want to try to find the one that gives you the lowest numbers possible. Okay. So in this case, we have three structures. We have a triple bond and we have a double bond. So where should I start counting from? To give me the lowest numbers possible.
The left side.
The right side.
That's a trick question, huh?
So 1, 2, 4, 5, 6, 7, 8. If I start counting from the other side,
Get 10.
1, 2, 3, 4, 5, 6, 7, 8. So my lowest number would be 2 on the black numbers. Or from the left side. My lowest number would be a 1. So which one is the lowest number? The 1. Okay, so the 1 is going to represent the last thing. Okay, since we have double bonds and triple bonds are equal to each other, it's going to be based upon who gives me the lowest number, right? So in this case, my lowest number is going to be the y, right? Okay. So the way that we do this is we're going to have to sit there and do it a little bit different. We got to put the numbers internally. So how many double bonds do we have? What double bonds located?
2 and 5.
Double bonds. Okay, so which numbers are we going to use? Because are we counting? Are we using the green numbers or are we using the black numbers? The green numbers, the lower, the numbers at the bottom.
Yes, that
So,
one.
okay.
7 and 6.
So there we go. So it's going to be N. Okay. Okay. Double bonds are located where?
I'm sorry.
Double bonds are located where?
Oh, 6.
4 and 6.
46.
4 and 6. Starts at the 4, starts at the 6. So we're going to put 4, comma, 6, dash. How many is that? How many double bonds is that? How many double bonds? do we
Oh,
have?
2.
Okay. So there are 2 double bonds. So that's 3 picks. Should I do these?
Die.
Die.
E. Oh.
Okay. So we're going to put die and we're going to put E. but we're just gonna put the E in. We're not gonna finish the E, okay? The last, where is the triple bond?
After one.
One, Y, N, E. Okay? And then the total number of carbons, 8. So then we use the prefix of what? Oct. So we're gonna use octa. Okay, so it's gonna be octa 4, comma 6 dash diene dash 1 dash 5. Okay. So this way you're telling me where everything is located and what it's located with, right? So tell me that there were 4 and 6 where we had the E and E, and there were 2 of them. That reminds me that there are 2, right? We know that the triple bond is located at the 1 carbon. Okay, so then we put Y and E. And then octa tells me that I have a total of 8 carbons altogether. Yes.
Okay. Double bonds?
Yeah.
Oh, okay.
That's number 2. And then just to clarify, the Y and E, that comes from the triple bonds?
That's right.
Okay.
Triple bond is always going to be YN or YNE. So if your double bond has the lowest number, then it's going to be E and E. Y and E. Okay. That's my opinion.
Okay.
Okay. What's the 1? The die. That's the 1. Yeah, that's the 1. Number 1. Guys, we're starting at 1.
And then more clarification, so the die is constituted of bonds, right? And then the N represents
No, it represents double bonds.
the double bonds.
Yes, so EN represents double bonds, or
Okay.
ENE represents double bonds.
Okay.
YNE represents triple bonds, ANE represents single bonds.
Okay.
Okay. Okay, are you guys good? Okay, I'm gonna put up a name, and you guys are gonna give the instructions.
Well, that was you.
Scala.
That was you. Yes. What happened with choice? I'm scared. Don't know, so. Does it matter where your points start? Like, does it have to be face up when you point start?
No.
Okay, so it can be face down, like if I go here.
It doesn't matter, as long as you have the right number. Right?
Okay,
You can start from the top or from the bottom.
okay, that's what it says.
You can either start down. Okay, you guys ready? Okay, what am I doing?
She has a good answer.
Okay, let's try.
Okay.
I want to see that. Let's go.
Okay, so we do one half triangle, or not, so one upside down V. The double bonds are both ends.
Oh, no, you had to write the first one.
This one?
Yeah, you had to write the first one.
Straight line, and then add, make it a triple bond.
No, like kind of like
Like at an angle,
Okay.
parallel triangles.
and
Oh,
then add the triple bond.
Triple bond.
okay.
And then do another end. Or
It has to be, yeah, it has to be.
Oh.
Yeah, but this is that. So it has to be like that.
oh yeah. Then you have to make another end for the 7. There we go.
Okay, so let's count. 1, 2, 3, 4, 5, 6, 7. Okay. So triple bond on the 4th, right? So 1, 2, 3, 4, starting at the 4th. Yeah, the double bond at the 3rd, that's the 7th.
So when it's triple bond, it has to be parallel.
It has to be linear.
What's that?
I did tell you that. Yeah, I know. Thanks. Yes, the triple bond has to be linear. It's always going to be. Yeah, so there has to be a space between. What is that? Push the button. Yes. Yeah. Yeah. Okay. Okay. So I think this is a good stop. Okay, so in terms of responsibility for the exam, we have gone over alkanes, alkenes, and alkynes. Okay, so it's going to be very brief. Very brief.
Little alkynes will not be
No, they won't. So look, regular. Those are going to be. the ones in the back. Okay. You guys have a good spring break. Study hard, work hard. Again, I'm going to open up all of these. So here's an opportunity to do things that you haven't done. Again, it'll actually open up tomorrow because I'm not going to go home.
And then for the labs, the assignments are due this week.
Your lab and assignments that were due this week. So the lab that technically would have been due on, I strongly recommend that you do it because it will help you with the exam.
So the last
That
lab 9.
Yep.
So that one, so you haven't posted lab 8 yet, have you?
I haven't put that. But there's, I don't think I have lab. They're both becoming.
Okay, I just want to make sure, I don't want to miss it. So, I work full time for midday, that's why I'm asking. And this one. Okay, so that's why I was just asking, okay.
So that's, well, nothing is going to be due the remaining of the week.
Okay.
And so technically it's not going to be due. So it'll be due for next Wednesday. Everything is going to be next Wednesday.
Okay.
What's that?
I said you would pull credit on all of them. No, come on, I've been handling it, I do.
That's a great idea. But doesn't mean I, you know.
What can, hey, what can you say?
Yeah.
I got good training.
Oh, have a good spring break.
Yeah, we'll see you.
Yeah, study hard,
Yeah.
study very hard.
Cordell, are there any questions before you? Yes, the tutors will be helping you during spring break. 2 hours that will be available, or two sessions that will be available during spring break. Not all of the tutors though, because they're on spring break as well too. And food. Yeah, because everything's on campus.
Yeah. Yeah.
Okay. And then I will try to have one day in the middle of the week where I hit one of my office hours. I'll let you know. We'll definitely do cocktail hours towards the end, not this first one.
Oh, okay, yeah.
Okay, Arnell and online folks, are you guys good? Can you guys hear me?
Can hear you. Hanging in there.
It's good. See you. So do you guys have any questions?
Do we have class on Friday?
No, you guys do not have class on Friday. I was told that you guys have, it's Cesar Chavez Day. You guys can by doing something for your community and take a picture of yourself doing it.
Okay, thank you.
You're welcome. Any other questions?
Oh, I'll go last.
Okay. Anyone else? Is there anyone else on the top, on the 16th back?
No questions. I'm good.
No questions? Okay. Four people left. Anyone else? Or they're just recording the lecture, that's all. Okay, we're down to 5, so that's 3 left. Okay, so go ahead, Alexis.
I just had a question regarding the molecular geometry. In particular, like one of the problems that you have CBr2I2. And we drew out the diagram where C is in the middle. And then the rest all have 7, right? So it's basically like just 4 lines coming out of carbon connecting the two I's and the 2 BRs.
Yep.
So that gives you 4 central atom bonding pairs and 0 lone pairs. So in terms of the electromagnetic what's it called? Negativity values. So you have carbon that's 2.6 and Br that's 3.0. And then you have iodine, I can't say it. It's 2.7, right? So to find the polarity, you subtract C from Br.
Yep.
Or Br from C, which would give you 0.4.
That's right, which means it's not polar, right?
Right, and then you would do it for Br and I as well?
No, you wouldn't do Br and I because they're not bonded together.
Oh, that's right, duh. Okay, so that gives you, right, okay, so that, I did put non-polar, so that gives you non-polar, right?
Okay.
And in terms of the symmetry, what gives you that answer again? It's how much they're pulling?
Yes, so is there any pulling? So if it's
No,
not,
it's all even, right?
that's right.
So it's symmetrical.
That's right.
Okay, and you get that answer from looking at the diagram and from the actual electronegativity values, right?
That is correct.
Okay. And then in terms of the molecular polarity, how do you get this again?
The molecular polarity,
Yes.
you just told me how you got it, right? Because you look at the overall molecule, right? So in this case, everything is pulling evenly, right?
Yeah.
So in other words, there's really no pulling going on, okay? Because they're sharing the electrons. Nobody's being favored.
Right.
So the overall molecule is going to be what?
Non-polar? But I guess my confusion comes with sometimes the bond polarity differs from the molecular polarity.
So I don't understand the confusion. There's no confusion. So you have to look at the bond polarity individually, but you look at the molecule as a whole, right? So let's say, for instance, we had fluorine here, right?
Yeah.
So you know that the bond C is going to be nonpolar, but you know that the polarity between the F and the C is going to be polar.
Oh, because 4.0 minus 2.6 gives you a polar.
That's right.
Oh, so when that means that there is a pull between
Yeah.
F and C.
It's going to be pulling in this direction.
Oh, okay.
The
So
whole-
that's when it differs, when you have to do different ones, right?
That's right.
Ah, okay. That was my question. Got you. Thank you so much. That was it for me.
Good questions.
Well, you have a good spring break. Enjoy your time with your family or friends.
I will. I will try. I'll do a lot of grading too, man. I got some.
Yep. Alrighty. Oh, and as for this lab, it's not due. You said you were kind of cutting off.
Yeah, I said it won't be due until Wednesday. Next Wednesday.
Okay.
We'll have a lot
Gotcha.
of stuff to do next Wednesday. So.
Right on. Right on. Okay. Sounds good. I'm out of here. Have a good rest of your week.
You too. Have a good night.
Bye.
Good night.
Good night.